Good morning, dear student. So again we are here with the new concept and the next concept in the mathematical physics. So in last lecture up to we have covered that differential equation, and in particular the how to solve that first order first degree differential equation, and there are various type of method using which we can solve that first order first degree differential equation. So next thing is that we are going to study that matrix algebra. So what we are going to study or what we are going to learn in that matrix algebra. So we will start from the basic definition of matrix, and then there are certain types of matrices. So we will go through that one by one, and then how to find out inverse of matrix. So there are also certain method with the usual method that you know that A inverse is equal to 1 upon determinant of A into adjoint of A. And then we have certain types of other method as well, that is Gauss-Jordan method, and then using Cayley-Hamilton theorem you can also find out inverse of matrix. So these are certain another method. Then we will go through the eigenvalues and eigenvectors, then also what is the relation between that eigenvalue and determinant of matrix, what is relation between eigenvalue and trace of matrix, and so on. So these are the certain topics that we are going to study in matrix algebra. So let us start with the definition of matrix. So what we mean by matrix? So in our daily life, we are everywhere we are using that matrix. So suppose if we go to that library, then the book arranged in that cupboard, that is also one of the example of matrix, because it is arranged in certain manner or arranged in certain order. So matrix is nothing but matrix is a arrangement of mn objects in rectangular form. Matrix is nothing but it is arrangement of mn elements in rectangular form, where m is the number of rows. That means we are arranging in m rows and n columns, and there are total mn elements. And matrix A generally written by A is equal to that Aij, where I denotes the particular row of the element and J denotes that column of the element, where 1 less than or equal to I less than or equal to M, and 1 less than or equal to J less than or equal to N. So here matrix with M rows and N columns can be denoted by A is equal to Aij, where I denotes that number row in which this element is lying, and J denotes that column in which this number is lying. So for example, suppose if you want to write that 3 by 3 matrix, then that we can write A11, that is first element, first row, first column, first element. Then A12, that is first row, second column. Then A13, that is first row and third column. Similarly, that A21, that is second row, first column. Then A22, that is second row, second column, and A23. Similarly, then A31, that is third row, first column. Then A32, that is third row, second column, and A33, that is third row and third column. So this is how we can write in general matrix. So in I think in 1827 the concept of matrix was introduced by J.J. Sylvester. Yes, this concept was introduced, the matrix concept was introduced by that J.J. Sylvester. And then after, one English mathematician has also explored this concept of, I forgot that name of that particular mathematician, but he has explored some more concepts related to the matrices. So matrix is nothing but it is an arrangement, or in particular we can say it as a rectangular arrangement of mn objects, where m denotes that number of rows and n denotes that number of columns. and this is, you can see that this is 3 by 3 matrix. So here in notation form you can write A is 3 by 3, where 3 denotes number of, first 3 denotes that number of rows in matrix, and second 3 denotes that number of columns. So in general this matrix can be written as AMN, where M is the number of rows and N denotes that number of columns. Clear? So in general that matrix can be written as AMN, where M denotes that number of rows and N denotes that number of columns. So now next definition, or next let us go through that certain type of matrices, so in which that first matrix is row matrix. When we can say that a matrix is a row matrix, so matrix which contains only one row, then it is said to be row matrix. So in particular a matrix for which that number of row is 1, and in particular if we write A as Mn, AMN be any matrix, so if the value of M is equal to 1 in particular, then we can say it as a row matrix, and we can write that row matrix as A11, A12, A13 up to A1n. This is the in general example of row matrix. So this is a matrix which has only one row and n columns, so this matrix is known as a row matrix. Clear? And similarly in particular if the value of n is equal to 1 and M in general you can take any positive natural number, then it will be the column matrix. That means column matrix can be written as A11, then A21, A31 up to AN1. Sorry, not N, but here M, because we are taking that M row. So here AM1. So here you can see that there is only one column, but there are M rows. A11, A21, A31 up to AM1. So this is known as a column matrix. So again let us repeat the definition. Row matrix means a matrix which has only one row, and column matrix, that means a matrix which has only one column. So this is row matrix and this is column matrix. And in general if we have A is an M by N matrix, so if we take M is equal to 1, then it will be reduced to row matrix, and if we take N is equal to 1, then it can be reduced to column matrix. Clear? Now definition of square matrix and rectangular matrix. So when we can say that a matrix is a rectangular matrix, so a given matrix A is matrix which is given as M by N, that means M rows and N columns, then it is said to be rectangular matrix if M is not equal to N. So rectangular matrix means M is not equal to N. If we have M is not equal to N, then it is said to be rectangular matrix, otherwise it is said to be square matrix. Square matrix means whenever we have that value of M and N both are equal. That means if we have same number of rows and columns in matrix, then the matrix is said to be square matrix, otherwise it is said to be the rectangular matrix, because whenever we write the matrix in which that M is not equal to N, then it will be something like that rectangular box for which that length and breadth both are different. So that's why it is known as a rectangular. And if we take that same number of rows and column, then if we write that matrix, then it will be like square, shape square, and so that's why from that we can say that it is a square matrix. So square matrix means a matrix in which the number of rows and number of columns are equal, otherwise it is said to be rectangular matrix. So generally or most often we are going to deal with that square matrices. So now whenever I am saying that matrix, so you need to consider it as a square matrix, and a matrix if we have that square matrix, then it can be only written as an. That means here A is a matrix of order n. Order n means it has n rows and n columns. So instead of writing that n cross n, you can also write that n cross n as well. So this is a matrix which contains that n rows and n columns, but also we can write it as an an. That means it is a matrix for which there are n rows and n columns. So this is the meaning of an. So this is also one of the notation to denote that square matrix. So now onwards, whenever we are saying that matrix, so you need to consider it as a square matrix. Whenever we are going to study about that rectangular matrix, then I will mention about that rectangular matrix, but now onwards you may consider any matrix as a square matrix, because for there are certain definitions for which we can also only apply if we have that square matrix. So now next definition is that zero matrix or null matrix. What we mean by that zero matrix or null matrix, whether it is a square matrix or rectangular matrix. But when we can say that a matrix is a zero matrix or null matrix. So matrix is said to be zero matrix or null matrix if each entry of the matrix are zero. That means suppose if I write that matrix A is equal to 0 0 0 0, then this is null matrix of order 2 or 2 by 2, which have 2 rows and 2 columns and each entries are 0. So this matrix is said to be zero matrix. You can say it as a zero matrix, or you can say it as a null matrix. You can say it as a null matrix. So matrix is said to be zero matrix or null matrix if each entries of the matrix are 0. Otherwise, if one of the entries not equal to 0, then we can't say it as a zero matrix. So for zero matrix, each entry should be 0. Then and then we can say it as a zero matrix. Now next we have there are certain another types of matrices. So in which first one is that upper triangular matrix and lower triangular matrix. First of all, we can define it only for the square matrices. So a square matrix is said to be upper triangular if all the entries below to the diagonal are 0. Suppose if we have 3 by 3 matrix A, B, C, D, E, F and G, H, I. Suppose this is a 3 by 3 matrix that we have. So when we can say that this is a upper triangular matrix, upper triangular matrix, and same kind of term that we have lower triangular matrix. This old definition that you already studied in 11-12 standard, but just I am repeating all the definition. So there are two terms related to that matrix, and in particular for square matrix, upper triangular matrix and lower triangular matrix. So when we can say that a matrix is upper triangular, so these entries are said to be the principal diagonal element. These entries we can say it as a principal diagonal element. These are, we can say it as a principal diagonal element. So a matrix is said to be upper triangular matrix if all the entries below to the principal diagonal are 0. That means the value of D, G and H are 0. Then we can say that that matrix is a upper triangular matrix, because you can see that this will form one kind of triangle on that upper side of the given matrix. This can form, suppose if we draw the line passes through that ABC, then AEI, then IFC, then it can form like a triangle. So that's why, and it is on upper side of the matrix, so that's why it is known as the upper triangular matrix. Similarly, a square matrix is said to be the lower triangular matrix if the entries above to that principal diagonal are 0. That means the value of B, C and F, these three are 0. This is for only for 3 by 3 matrix, but you can generalize it for that n by n. So that's why I'm saying that general definition, that if all the entries above to that principal diagonal are 0, then it is said to be lower triangular, because if you draw the line passes through ADG, then GHI, then IEA, then it will be one kind of triangle which is on that lower side of that matrix, and so that's why it is lower triangular matrix. So again I am repeating the definition of these two. Upper triangular means all the entries below to that principal diagonal are 0, then it is said to be upper triangular, and if all the entries above to that principal diagonal are 0, then it is said to be lower triangular matrix. Clear? So this is this is also the type of matrices. Then we have next type is the diagonal matrix. What we mean by the diagonal matrix? So matrix is said to be diagonal if all the entries other than diagonal are 0. That means except A, E, I, all the entries above to that principal diagonal and below to that principal diagonal all are 0. Upper triangular, lower triangular. Upper triangular in which that below to diagonal 0, lower triangular means above to that diagonal are 0. But in diagonal matrix, all the entries are 0 except that principal diagonal. Other than principal diagonal entries are 0. If that AEI is also 0, then it is also said to be the diagonal matrix. Suppose if someone might say that, suppose if I consider that matrix with all the entries are 0, 0, 0, 0, then 0, 0, 0, 0, 0, 0, then this is also the diagonal matrix. This is also the diagonal matrix. Zero matrix itself is a diagonal matrix, because the definition says that all the entries other than principal diagonal are 0. There is no anything given about that principal diagonal entry. Principal diagonal entry can be 0. Principal diagonal entry can be non-zero as well. So if all the entries except the principal diagonal are 0, then it is said to be diagonal matrix. Otherwise it is said to be non-diagonal if one of the entry other than principal diagonal is non-zero. Now next we have first of all, let me just tell you about the determinant. So I hope that everyone is aware about that, how to find out determinant of 2 by 2 matrix and 3 by 3 matrix. So first of all, let me just going to explain that determinant of matrix. So suppose if we have first 2 by 2 matrix, suppose if we have that A, B, C, D, this is a 2 by 2 matrix, then determinant of A, this is determinant of A, not mod of A. Please remember it carefully. This is known as determinant of A, not mod of A, because mod can be applied on number, not on any matrix. So this is the notation for determinant of A. So determinant of A, that means it is determinant of this matrix A, B, C, D, and here we have to take that cross multiplication AD minus, sign is minus, and then C into D. So AD minus BC, sorry, it is not CD, it is BC. So this is how we can find out the determinant. Suppose if we have that A is equal to the matrix 1, 2, 3, 4, then determinant of A, that is determinant of 1, 2, 3, 4. So it is 4 into 1, so it is 4 minus 2 into 3, that is 6, so it is minus 2. So minus 2 is the determinant of the given matrix. So for 2 by 2 matrix, determinant of A will be AD minus BC. So this is how you can find out determinant of 2 by 2 matrix. Now suppose if we have that 3 by 3 matrix, A is a matrix in which there are 3 rows and 3 columns, and also let me just explain that we can only find out determinant of square matrices. That means a matrix with same number of rows and same number of columns. So suppose if we have A is a matrix A, B, C, D, E, F and G, H, I, then determinant of A is equal to the determinant of A, B, C, D, E, F and G, H, I. Then it will be, first there are position sign for each element. So position sign you can give it by minus 1 raised to I plus j, where I denotes the place in which, I denotes that row in which that number is located, and j denotes that column in which that number is located. So suppose if we consider that first element, then it lies in the first row and first column. So 1 plus 1, so it is 2, minus 1 raised to 2, so it is plus. Now second element, so this element is in first row and second column, so 1 plus 2, so it is 3, minus 1 raised to 3, that is minus 1. C, that is element of first row and third column, so 1 plus 3, so it is 4, and minus 1 raised to 4, that is plus. This is how we can find out that position sign. Similarly, this is the element of second row first column, so it is 2 plus 1, 3, so it is minus 1 raised to 3, minus 1. Then this is the element of second row second column, so 2 plus 2, 4, minus 1 raised to 4, that is plus. This is the element of second row third column, so 2 plus 3, 5, minus 1 raised to 5, that is minus 1. Now this is the element of third row in first column, so 3 plus 1, 4, minus 1 raised to 4, that is plus 1. Then this is the element of third row second column, 3 plus 2, 5, minus 1 raised to 5, that is minus 1. And last one is that element of third row third column, so 3 plus 3, 6, minus 1 raised to 6, and that is plus. So this is how we can give that position sign to each of the element. Now let us take that particular element with its sign. So A is a sign positive, so A into, now neglect the column and row in which A lies. Now just we need to neglect that row in which A is lying, and also we need to neglect that column in which A is lying. And now we need to take the determinant of this remaining 2 by 2 matrix. So determinant of this remaining 2 by 2 matrix is EI minus HF. EI minus HF. Now B with the sign minus, now remove that column in which B is lying and also row in which B is lying. So now we need to take the determinant of remaining 2 by 2 matrix, so it is DI minus GF. And at last plus C into that remove column in which C is lying, remove row in which C is lying, and now we need to take the determinant of this 2 by 2 matrix, so DH minus GE. DH minus GE, and by expanding this we can find out the determinant of this 3 by 3 matrix. By expanding this we can find out the determinant. Okay, and also we can find out adjoint matrix from this as well, because we know that inverse of any matrix that is given by 1 upon determinant of A into adjoint of A. So adjoint A, that means it is a transpose of minors of that matrix, or cofactor. Instead of minus we are just using that cofactors. So adjoint of A, that is the transpose of cofactors of the given matrix. So cofactor means it is EI minus HF, that is the cofactor of A. then minus di into minus gf, that is the cofactor of b, and similarly you can find out that cofactor for other elements as well. So A inverse is equal to 1 upon determinant of A into adjoint of A, where determinant of A that you can expand by this way. So let us take one example to find out the determinant. Let us take one example. So let us take that 1 2 3, then 1 0 1 0 1 0. Suppose this is the matrix, and now we want to find out the determinant. So determinant of A, that is 1 2 3, then 1 0 1 and 0 1 0. So now this is plus minus plus. So first plus 1, then neglect column and row in which 1 is lying, so it is 0 minus 1, so that is minus 1, minus 2, neglect that column and row in which 2 is lying, so 0 minus 0, so it is 0, and at last it is 3, neglect that first row last column, so it is 1 minus 0, so it is 1, and so this is minus 1, this is minus 2 into 0, so it is 0, and plus 3 into 1, so it is plus 3, so 3 minus 1, and that is 2. So 2 is the determinant of that given matrix. Clear? So 2 is the determinant of given matrix. And now from the determinant we have one more definition, that is that definition is for singular matrix and non-singular matrix. So a matrix is said to be singular matrix. A matrix is said to be singular if it has determinant as a 0. A matrix is said to be singular matrix if it has determinant 0. And a matrix is said to be non-singular if the determinant of A is not equal to 0. And also in place of non-singular you can say it as a invertible. Matrix is said to be invertible if determinant of A is not equal to 0. Invertible means a matrix for which we can find out inverse, because if determinant is not equal to 0, then and then we can apply the formula to find out inverse, that is A inverse is equal to 1 upon determinant of A into adjoint of A. So then and then we can find out the inverse, otherwise we can't. So determinant of A is not equal to 0, then matrix is said to be invertible. This is both the way true, because it is necessary and sufficient condition that matrix is invertible if and only if its determinant is not equal to 0. If we have a matrix with determinant 0, then it is not invertible and it is said to be a singular matrix. So matrix with determinant 0 is said to be singular, and matrix with determinant non-zero is said to be non-singular, or you can say it as a invertible. Invertible matrix means a matrix for which we can find out the inverse. Clear? So these are the certain definitions related to matrix. Now next definition is that transpose of matrix. What we mean by the transpose of matrix? The transpose of matrix, you can define it for that square matrix as well as for rectangular matrix as well. So a matrix can be converted, or matrix can be converted by taking that rows into column and column into rows. Suppose if we have that matrix A is equal to that, let us take 3 by 3 A B C D E F and G H I, then transpose of matrix is denoted by A power T. Transpose of matrix is denoted by A power T, and it is defined by just transforming the rows of or columns of the given matrix to row and rows of the given matrix to column. So here we can say that ABC is the first row, so we need to write it into the column form ABC. So rows just we are transforming into column, or you can say it we are transforming the column into the row. So first row become that first column, second row become that second column, D, E, F, and that last row become that last column, so G, H, I. So G, H and I. So this is the transpose of the given matrix. So transpose of given matrix can be getted by just transforming rows into columns or columns into row. So because if you transform that row into column, then automatically column will be converted to rows, because you can see that here ADG is the first column, so in transpose ADG is the first row. Similarly ABC is the first row, so ABC is the first column. So the transpose of matrix can be getted by just transforming row into column, or here I am using the word or columns into row. So this is how we can define the transpose of matrix. Now next definition is that identity matrix. So what we mean by that identity matrix? So a matrix is said to be identity matrix if every element other than principal diagonal are 0 and every principal diagonal entry are 1. That means suppose if we have A is a matrix, then every principal diagonal entry should be equal to 0, and this is defined for only square matrix, and principal diagonal entry should be 1. So 1 0 0, then 0 1 0 and 0 0 1. This is said to be the identity matrix. This is the identity matrix, or you can say it as a unit matrix. So identity matrix is a matrix in which every principal diagonal entries are 1 and all other entries are 0, and this is also the matrix with determinant is equal to 1, because if you find the determinant, then 1, neglect that column row, so it is 1 into 1 minus 0, so it is 1, and so 1 into 1, and that will give us 1. So determinant of identity matrix will be always 1, and it is a matrix for which that principal diagonal 1, other entries are 0. Now suppose instead of principal diagonal entry 1, suppose if we take any arbitrary number k, suppose instead of 1, suppose if we take that k, where k belongs to R, you can take 1 as well, then these kind of matrix are said to be scalar matrix. These kind of matrix are said to be scalar matrix. So matrix is said to be scalar matrix if all the principal diagonal entries are any constant number and they are same, and other entries are 0. And suppose these entries are not same and they are distinct, then it is said to be diagonal, because already we have defined what is diagonal matrix. So a matrix is diagonal if all the entries other than principal diagonal are 0. So here this scalar matrix is also diagonal, identity matrix is also diagonal matrix, and suppose if you take in scalar matrix, you can if you take that all the principal entries are different, then it is also the diagonal matrix. Clear? Now next we have that orthogonal matrix. What we mean by that orthogonal matrix? So let us go through that what is orthogonal. So a matrix A of order n, that means here we are considering that square matrix. So matrix A of order n is said to be square matrix if A into A transpose, that means this is the multiplication of matrix and that will become identity matrix. And I hope that you all of are aware about that how to multiply two matrices. So just let me again explain by considering one example, that suppose we have 2 by 2 matrix. A is equal to ABCD and B is equal to that XYZW. Then A into B, so it is A, B, C, D, then X, Y, Z, W. So now first entry will be, here we need to consider that first row and here we need to consider that first column. So now let us take multiplication of A with X, so it is AX, plus let us take multiplication of B with Z, so it is BZ. So this is the first entry in the multiplication of two matrices AX plus BZ. Now for that second entry, let us consider the second column. So again we need to take that multiplication of A with respect to Y, so it will be AY plus multiplication of B with respect to W, so it is BW. So these are the two entries of that multiplication. Then now for that second row, let us consider here second row of matrix A, and again let us consider that first column of matrix B. So let us take multiplication of C with respect to X, so it will be CX, plus let us take multiplication of D with respect to Z, so it is DZ. That will give us the third entry. And for that last entry, let us consider this second column again, then it will be C into Y, then it will be CY, plus let us take multiplication of D with respect to W, so it is DW. And this is how we can find out the matrix multiplication. And for matrix multiplication, it is not needed that two matrices should be square matrix. For matrix multiplication, it is not compulsory to take two square matrices, but for the necessary and sufficient condition for the matrix multiplication is that, suppose if we have A is a M by N matrix and B is a P by Q matrix, then so if we want to find out A into B, then number of columns in the first matrix and number of columns in the number of rows in the second matrix, that should be same, that is N is equal to P. So if N is equal to P, then and then only you can find out AB, and if you can find out A into B, then N should be same as P. And suppose if we want to find out BA, then the column of first matrix, that is Q, and number of rows of that second matrix, that is M. So for that Q should be same as M, and this is also the second way true. Clear? So now let us consider that type of example here. Suppose if we have A is a matrix 1 2 3 0 1 0. This is the matrix which contains that 2 rows and 3 columns, and consider that B is the matrix 1 0 0 1 and 1 1, and this is the matrix which contains that 3 rows and 2 columns. So suppose if we want to find out A into B, then the number of columns of the first matrix and number of rows for that second matrix are same, so A into B is possible. So now let us find out. 1 into 1. So first entry will be that 1 into 1, 1 into 1 plus 2 into 0, that is 0. So 1 plus 0 plus 3 into 1. So it is 3. Now second entry is 1 into 0. So it is 0 plus 2 into 1. So it is 2 plus 3 into 1. So it is 3. Now next second row. So 1 into 0. So it is 0 plus 1 into 0. So it is 0 plus 0 into 1. So it is 0. Now second column, 0 into 0. So it is 0 plus 1 into 1. So it is 1 plus 0 into 1. So it is 0. And this is 2 by 2 matrix. And where that 2 by 2 comes, so the A into B will be the matrix in which there are 2 rows and 2 columns. So that new matrix will be same as, or it having the same number of rows as of matrix A and same number of columns as of matrix B. So that 2 by 2 comes from that, 2 comes from that A, that means number of rows come from A and number of column come from B. So let us simplify it. Then it will be 1 plus 0 plus 1, so it is 4, 0 plus 2 plus 3, so it is 5, 0 plus 0 plus 0, so it is 0, and 0 plus 1 plus 0, so it is 1. And this is the new matrix A into B. So for matrix multiplication, the matrix need not be square always. For matrix multiplication, matrix need not be square always. You can take a matrix in which the number of columns in the first matrix and number of rows in the second matrix are same, then you can take product. So here I have given that both the condition for AB and B. Clear? Similarly, you can in this you can find out BA as well, because suppose if we consider that BA, then B is first and A is second. So B that contains 2 columns and A that contains 2 rows. So here 2 is equal to 2, and so resultant matrix will be 3 by 3. So BA will be 3 by 3 matrix. So you can also find out BA as well. Clear? So this is how we can find out the product of matrix. So now again let us go through the definition that we are studying, is that orthogonal matrices. So what we mean by that orthogonal matrices? So matrix is said to be orthogonal if A into A transpose is equal to identity matrix. If the product of matrix with its transpose is identity, then that particular matrix is said to be orthogonal. And identity matrix itself is an orthogonal matrix. How? So suppose let us take that A is equal to the 2 by 2 identity matrix 1 0 0 1. Then let us find out transpose. So A transpose will be same as identity, because 1. Let us write that first row in first row in first column, or first column in first row. Then 1 0 will be written as in row 1 0, and then second column can be written as 0 1, and that you can say it is same as A. Now let us find out A into A transpose. So it is 1 0 0 1 into 1 0 0 1. So now first entry will be 1 into 1, that is 1 plus 0, so it is only 1. Then 1 into 0 plus 0 into 1, so it is 0. 0 into 1 plus 1 into 0, so it is 0. And 0 into 0 plus 1 into 1, and that is 1. And that is nothing but the identity matrix of order 2. That means 2 by 2 identity matrix. So identity matrix itself is a orthogonal matrix. So a matrix is said to be orthogonal if A into A transpose is equal to identity matrix. That means the product of matrix with its transpose, if it gives us identity matrix, then it is said to be orthogonal matrix, otherwise not. Now next definition is that symmetric matrix. What we mean by that symmetric matrix? So a matrix is said to be symmetric matrix. So what we mean by that symmetric matrix? So a matrix A of order n, that means we are considering that square matrix. A matrix A is said to be symmetric if it is same with its transpose. That means if A is equal to A transpose, then the given matrix is said to be symmetric. That means by converting that row into column and column into row, matrix doesn't change at all. There is no any change in matrix by converting row into column or column into row, then it is said to be symmetric matrix. Now let us take one example. So suppose if we have that A is equal to the matrix 1 2 2 1. Let us take one example. A is equal to 1 2 2 1. So let us find out the transpose of this matrix. So let us write first column as a first row. So it is 1 2 and 2 1, and this is nothing but matrix A. So this is the this is the symmetric matrix, because for which A transpose is A itself. So that's why it is said to be symmetric matrix. Now the next definition is that skew symmetric matrix. When we can say that a matrix has a skew symmetric matrix, so a matrix is said to be skew symmetric if A is equal to minus A transpose. A is equal to minus A transpose. There is just one change in the definition of symmetric. In symmetric we have A is equal to A transpose, but in skew symmetric we have A is equal to minus A transpose. So let us take one example of skew symmetric matrix as well. So suppose if we have A is a matrix 0 1 minus 1 0. So let us find out the transpose. So transpose means we can write the column into row. So 0 minus 1, that will become first row, and 1 0, that will become second row. Now whenever we are taking something common from the matrix, then we need to take common from each element of the matrix. So suppose let us take minus 1 common from matrix, then we need to take minus 1 common from the every element. So it will be 0 1 minus 1 0, because minus 0 or 0, that is same. Minus 1 common, so there is only 1, and minus 1 we are taking common, so here we need to multiply it by minus 1, or we need to divide it by minus 1, so it is minus 1. But this is nothing but the matrix A itself. This is the matrix A. So A transpose is equal to minus A, or you can write that A is equal to minus A transpose by multiplying by minus 1 on both the sides. A is equal to minus A transpose. So A is equal to minus A transpose, and that's why this matrix is said to be skew symmetric matrix. Now one more thing that I want to just you have to remember for that skew symmetric matrix is that the principal diagonal entries of skew symmetric matrix will be always 0. In skew symmetric matrix, principal diagonal entries are always 0. And why it is 0? Because A is equal to minus A transpose, that means we need to take some minus common from each entry. So whenever we will take that minus common, So suppose if we have here non-zero entry, then it will be changing to that negative of that given number, and that never give us the given matrix. Suppose if we have here 1, and if we convert A transpose, then here it will be 1. So now whenever we take that minus common, then here it will be minus 1. So minus, suppose if we get here minus 1, then we cannot write it as matrix A, because in matrix A we have plus 1, and here we are getting, after taking minus 1 common, here we are getting that minus 1. So instead of that, this matrix you cannot write A. So that's why in skew symmetric matrix, the principal diagonal entries are always 0. Clear? So this is about the symmetric and skew symmetric. Again, I'm just repeating definition. A matrix is said to be symmetric if it is same as its transpose, that means A is equal to A transpose, and a matrix is said to be skew symmetric if A is equal to minus A transpose, or you can write that A transpose is equal to minus A. This is also the definition that you can write by multiplying on both sides by minus 1. So that is skew symmetric matrix. Now the next is that I think somewhere you might have seen questions related to that next topic as well, and that topic is rank of a matrix. Rank of matrix. Rank of matrix means what? That matrix, for the given matrix, how many rows or how many columns are linearly independent. That means how many rows and how many columns are not dependent on each other. That is what we mean by that rank of matrix. So rank of matrix, there are certain methods to find out rank of matrix, and there are so many methods using which you can find out rank, but that are too lengthy process. One of the method is row echelon form, that you can find out the row echelon form of matrix, and directly from that matrix you can say that there are n number of linearly independent rows, and so that's why the rank of matrix will be n. But that is too lengthy process. It will take that 1 or 2 pages to find out a row echelon form or reduced row echelon form. So I am just giving you one hint related to find out the rank of matrix, and I think you might get that maximum 3 by 3 matrix or 2 by 2 matrix to find out the rank. So suppose A is a matrix of order n. Order n means it has n rows and n columns. Then rank of A, that is denoted by row of A, and that is n, if and only if the determinant of A is not equal to 0. If determinant of A is not equal to 0, then rank of A is equal to n. That means what is the n is the order of that matrix. And if determinant of A is equal to 0, then rank of A will be strictly less than n. Strictly less than n. And rank of A can be 1, 2, 3, 4 up to n minus 1, but it cannot be n, as a determinant of A is equal to 0. So whenever you have questions related to find the rank of matrix, So just find out the determinant of matrix. If determinant is not equal to 0, then rank is same as order, and if determinant is equal to 0, then rank is same, not same, but rank will be less than that particular number. So suppose if we have that 3 by 3 matrix for which determinant is not equal to 0, then rank is equal to 3. And suppose if you get that determinant is equal to 0, then rank will be strictly less than 3. That means might be of rank 1 or rank 2. But now how to find out that it will be of rank 1 or rank 2? So let me explain that how to find out precisely that it is of rank k, where k is between that 1 to up to n minus 1. So let us understood it by taking one example. So suppose if I am taking that A is a matrix which is 3 by 3, 1 0 0 0 1 1 and 1 1 1. Suppose this is the matrix. Now let us find out the rank of this matrix. So first of all, let me find out the determinant. So determinant of A, that is determinant of one 0 0, then 0 1 1 and 1 1 1. So now 1 into, neglect that first column and first row, so it is 1 into 1, 1 into 1, so it is 1 minus 1, and that is 1 into 0, and so it is 0. So here we are getting determinant as a 0, so rank will be definitely less than 3. Rank will be definitely less than 3. So now the question is that how to find out rank precisely, whether it is 1 or 2. So what we are going to do, so just neglect one of the row or one of the column of matrix. So suppose A is a matrix given as 1 0 0 0 1 1 and 1 1 1. So now just neglect one of the row of this matrix. So suppose here I am neglecting this row. I am just neglecting that first row. And now let us form one 2 by 2 matrix. Let us form one 2 by 2 matrix and find out the determinant of that particular matrix. So what is determinant of this matrix? So 0 into 1 minus 1 into 1. So it is 0 into 1, that is 0, minus 1 into 1, that is 1, and that is minus 1. So here we are getting non-zero number. Here we are getting non-zero number. Suppose someone say that I want to consider these 2 by 2 matrix, then let us find out the determinant. Determinant 1 1 minus 1 into 1, so it is 0. So that determinant is 0, but so that you need to neglect. That means you don't need to consider either this row or this row. Whenever we will get as determinant 0, then one of the row you need to neglect and you need to consider that remaining row or remaining column. So suppose you have considered that first as a second and third column, 1 0 0, that we have already neglected, then 0 1 1 and 1 1 1. And suppose you consider these 2 by 2 matrix for which we are getting determinant 0. So either neglect this column or this column, and suppose if you neglected this one, then find out the determinant of remaining 2 by 2 matrix. 0 into 1, that is 0, minus 1, and that is minus 1. So here you are getting determinant is not equal to 0. That means this is the matrix of rank 2. This is the matrix of rank 2. Clear? Suppose someone might say that I don't want to neglect that first row. Suppose if you neglect that second row, then by same way just you need to consider one of the 2 by 2 matrix Suppose 1 0 1 1, so 1 1 minus 0, so determinant is 1, and so which is not equal to 0, so rank is equal to 2. Suppose someone might consider this matrix 0 0 1 1, so that will gives us determinant 0, because 0 into 1 0 minus 0 into 1, that is 0. So either you need to neglect these two term or these two term, and you need to take the 2 by 2 determinant of remaining 4 entries, and that we are getting as a 1. So that will gives us rank is equal to 2. And suppose again, you might get that determinant of every 2 by 2 matrix is 0, then last rank by default it will be 1, because rank will be at least 1 for any of the matrix except 0, because 0 matrix has rank 0, but other than 0 matrix every matrix has rank at least 1. So suppose if you are getting every 2 by 2 matrix of rank determinant 0, then last the rank will be 1. Clear? So if the square matrix is given, then precisely you can find out by this way. And why that rank is equal to 2? Now here we have calculated that rank is equal to 2. Why that rank is equal to 2? That means there are only 2 linearly independent row in the given matrix, and also that you can see here third row is dependent, or it can be written as a linear combination of first two. So suppose if I am writing that last row, then last row can be written as summation of these two, 1 0 0 plus 0 1 1. This is first row, this is second row, and this is third row. So third row can be written as linear combination of first two. Clear? So this is how you can write this is how you get that rank is equal to 2. That these two are the only independent column, they are not dependent on each other. From these you can't get this, or from this you can't get this, but from these two you get that third row. So that's why it is of rank 2. Clear? And similarly, directly from column you can see that second and third column both are equal. Directly from the matrix you can say that second and third column both are equal. So from these two we can consider rank only 1, because this is the multiple of this, or this is a multiple of this, by k is equal to 1. This can be written as 0 1 1 is equal to 1 times 0 1 1. So 1 is second column is multiple of third, or third column is multiple of second. So this will give the rank 1. This is only considered as a 1, and this is considered as a second. So this will give rank 1, this will give rank 1, and total rank will be 2. In informal ways, not from that direct, but it is in informal ways. Clear? So this is how we can get that rank is equal to 2. So again I am repeating, rank of matrix means if the given matrix is of determinant non-zero, then the rank of matrix will be same as the order of matrix. But if the determinant is equal to 0, then you need to consider first, if A is of order n, then you need to consider the determinant of order n minus 1. If again you are getting the determinant of n minus 1 is 0, then you need to consider that another n minus 1 determinant, and if you are getting the determinant non-zero, then rank will be n minus 1. Again, if each determinant of order n minus 1 gives the value 0, then you need to consider the determinant n minus 2. determinant of order n minus 2, and if one of the determinant will give the non-zero value, then rank will be n minus 2, and if all the determinant of order n minus 2 will give value 0, then you need to consider for n minus 3, you need to check it for n minus 3 and so on up to that 1. Clear? So I hope it is clear to everyone related to the rank of matrix, and you can now solve some questions from that GSET paper or from that NET paper related to the matrix rank of matrix. You might get that example. So a matrix, so in short, a matrix with determinant not equal to 0, it is of rank same as its order, and if determinant of matrix is equal to 0, then rank will be less than its order. Clear? So this is all about today's lecture. Next we will calculate some more examples related to that rank, and then after we will go for that eigenvalue and eigenvector, then Cayley-Hamilton theorem, and so on. Clear? So goodbye.